In our previous lesson, we explored how ideal gases behave and how pressure, volume, and temperature are linked by the ideal gas law. Let's now review the different forms of this equation, each useful in different situations. This is the density form, where we express the relationship using mass density. Next, we have the specific volume form, which focuses on volume per unit mass, often useful in fluid mechanics. Here's the molar form, where we calculate properties based on total moles or total mass. And finally, the molecular form connects directly to the number of molecules and Boltzmann's constant, useful in statistical physics. These forms give us flexibility, depending on whether we're studying gases from a macroscopic or microscopic perspective. Now, let's move forward. Let's zoom into the microscopic world of an ideal gas. Here, particles move randomly, colliding with the walls and each other. Here we see just particles moving around randomly, colliding with the walls and with each other. In an ideal gas, these particles are in constant motion. The internal energy of an ideal gas comes entirely from this molecular motion, specifically from the kinetic energy of its molecules. Let's break this energy into its different components, which are key to understanding heat capacities. Let's start with translational energy. This is the energy associated with the movement of the entire molecule through space. It's the kinetic energy from position changes as molecules travel from one location to another. In fact, the average translational energy of all the molecules is directly related to temperature. As we heat the gas, particles move faster, raising this energy. But molecules don't just move in straight lines. Some can also spin. This is called rotational energy. For diatomic molecules like hydrogen, they can rotate around axes perpendicular to the bond between atoms. This spinning also stores energy. Finally, let's explore vibrational energy in detail. This is the energy associated with the stretching and compressing of bonds between atoms for diatomic molecules like hydrogen. This involves the atoms moving back and forth along the bond axis. Vibrational energy becomes important at high temperatures, when molecules have enough energy to excite these vibrations. Together, translational, rotational, and vibrational motions make up the microscopic energy of a gas. Now that we understand these different types of motion, we're ready to see how they affect heat capacity, how much energy a gas needs to change its temperature. Now that we understand the different ways molecules store energy, let's build the next concept. Enthalpy. Enthalpy helps us simplify energy calculations, especially when gases are allowed to expand. We define enthalpy as H equals E plus PV, where E is the internal energy, everything happening inside the molecules. PV is the energy required to make room for the system, that is, the work needed to push against the surrounding pressure to occupy space. Why do we need this new quantity? Because many real-world processes happen at constant pressure. For example, heating air in an open room or boiling water in a pot. In these cases, it's much more convenient to track enthalpy rather than internal energy alone. Now, let's define heat capacity. Heat capacity is the amount of energy needed to raise the temperature of a substance by 1 degree. It's a measure of how much energy a substance can store mathematically. We write C equals delta Q delta T, where Q is the heat added to the system and T is the temperature change. There are two ways to talk about heat capacity. Total heat capacity, which applies to the entire system. Specific heat capacity, which is per unit mass of material. This distinction helps us compare different substances regardless of how much material we have. Let's first consider a process at constant volume, where the container is rigid and the gas cannot expand. In this case, no work can be done because volume doesn't change. All the heat goes directly into increasing internal energy. We define specific heat at constant volume as CV equals delta Q delta TV equals delta E delta TV, and total heat capacity at constant volume as CV equals delta Q delta TV equals MCV. Similarly, for constant pressure, we have specific heat capacity CP and total heat capacity CP. Now let's examine a constant pressure process. When pressure is constant, the gas can expand as we add heat. Part of the heat increases internal energy, but some of it goes into doing expansion work. Here, enthalpy becomes very useful because at constant pressure, dQ equals dH. Hence, we define specific heat at constant pressure as Cp equals delta Q delta Tp equals delta H delta Tp, and total heat capacity at constant pressure as Cp equals delta Q delta Tp equals mcp. For an ideal gas, the relationship between specific heat capacities involves the gas constant R, while the total heat capacities involve mass times R. For an ideal gas, PV equals nRT. The derivative of PV with respect to T at constant pressure is nR. Substitute into the heat capacity relation to get Cp equals Cv plus nR, or per mole, Cp equals Cv plus R. The heat capacity ratio gamma is very important for many thermodynamic processes. In a constant volume process, we fix the volume of the container. Let's examine how this affects the thermodynamic equations. As we add heat to the system, since the volume cannot change, all the energy goes into increasing the internal energy of the gas. This is shown by the increasing temperature and molecular motion. In a constant pressure process, the pressure remains fixed while the volume is allowed to change. This process is described by a different set of equations that account for both internal energy changes and the work done in expanding the gas. As we add heat to the system, the gas expands to maintain constant pressure. The specific heat capacity Cp is larger than Cv because the system needs additional energy to perform the expansion work while achieving the same temperature change. Now that we've seen both processes individually, let's reset and compare them side by side. Let's examine both processes simultaneously to understand their key differences. On the left, we have the constant volume process, where all heat input goes into increasing the internal energy. On the right, we have the constant pressure process, where the heat input is split between internal energy and expansion work. As we add the same amount of heat to both systems, observe the differences. The constant volume process reaches a higher temperature since all heat goes into internal energy, while the constant pressure process reaches a lower temperature as some energy is used for expansion work. Let's understand why gamma, the ratio of specific heats, is always greater than 1. Since Cp equals Cv plus the gas constant R over mass, Cp is always larger than Cv. For our diatomic hydrogen gas, gamma equals 7/5 or 1.4, which represents the additional energy needed for expansion work at constant pressure. This fundamental property, gamma greater than 1, is crucial for many thermodynamic processes, including the efficiency of heat engines and the behavior of shock waves. Let's solve a real-world problem. Consider a rectangular room with dimensions 5 meters by 7 meters and a height of 3.3 meters. The air inside is at atmospheric pressure and 25 degrees Celsius. Calculate the internal energy and enthalpy of the air in the room. First, we calculate the room volume. This tells us how much space the air occupies. Using the ideal gas law, we can find the mass of air in the room. At atmospheric pressure and room temperature, we have about 138 kilograms of air. For internal energy, we use E equals mCVT. The specific heat at constant volume represents the energy needed to raise the temperature when we don't let the gas expand. Finally, enthalpy adds the potential for the gas to do work. That's why we use Cp instead of Cv. The difference, R, represents the additional energy available for expansion work. Our calculations show that the internal energy is 2.92 times 10 to the 7th joules, and the enthalpy is 4.08 times 10 to the 7th joules. The difference between these values represents the potential work energy stored in the gas under constant pressure conditions. Before we continue, let's remind ourselves what is actually happening inside the gas when we add heat. Heat increases the speed of the molecules. That's the internal energy increase, but if the gas is allowed to expand, some of this energy also gets used to push against the surrounding pressure. This is the work term. This balance between energy going into molecular motion and expansion is exactly what the first law describes. The first law of thermodynamics is a formal statement of the principle of conservation of energy as applied to thermodynamic systems. These ideas form the foundation for everything that follows in thermodynamics, from heat engines and refrigerators to atmospheric science and chemical reactions, and, at the center of it, all stands the first law of thermodynamics, the universal rule that energy can change form between heat, work, and internal energy. But it can never be created or destroyed. Understanding this law gives us the power to analyze, predict, and control energy transformations in the physical world.